All right, 6.7, complex numbers. This is a whole new ball of wax for some of you. Some of you have used complex numbers before, some of you have not. But another way that we talk about complex numbers is we call them imaginary numbers. And, you know, some of you think math is hard enough with real numbers, and now we're throwing in ones that don't even exist. So, a number such as the square root of -9 is considered an imaginary number because there is no number multiplied by itself that will give you -9. If we put -3 times -3, two negatives give you a positive. So there's no way we can multiply the same numbers times each other and get a negative number. So that being the case, these are called imaginary numbers or complex numbers. Now, believe it or not, these are useful. It's not just trying to come up with more math for you, but it does let you expand your work with radicals and use things when you have a negative radical. So what this is we have another symbol that we're going to use, the letter I, and that represents an imaginary number. So what that does is that represents the square root of -1. So if I had the square root of -3, the negative part of that would leave and turn into an I, and we're left with a 3 in there. So pretty much what we're doing is we're taking the negative out and saying that it is an I. Okay, because our -1, actually, maybe a better way of saying this, maybe it helps to understand it better, is if I take this, that's also equal to, right? And that equals, and if the square root of -1 is I, then I just write I, and I have the square root of 3 left over. So the square root of -3 is I, square root of 3. Now you'll see some books write this as the square root of 3I. It just kind of depends. It doesn't matter which order they go in. It's just important to understand that that's what we're doing. All right, so let's look at a couple practice ones. So if it helps, -1 under a radical is equal to I, and then we have the square root of 25, so that gives me a 5. And when it's that way, then you automatically change it to 5I. Usually you set your I after the number. Okay, so something like square root of -12. That equals, and the reason I did 3 times 4 instead of 6 times 2 is because I wanted one of the numbers to be able to take the square root of, so that I could at least pull that one out. I'm going to pull the I out, and I'm left with that. Now you can check to see if this equals this by squaring the whole thing. So 2 times 2 is 4I squared, and the square root of 3 squared is a 3, and that equals 12I squared. Now here's one of the things that you'll learn. I squared is always equal to -1. So if that's the case, this is -1, which equals -12, which is what we started with there. All right, so I just said that square root of -1 equals I. I just told you that -1 by itself is equal to I squared. We also have I cubed, and that equals -I, and I to the 4th is equal to 1. This is very, very important to remember because there may be times where I say, what is I to the 30th power? Okay, so if I give you that, there's a really cool trick. I don't think the book talks about it, so this is just from me, and it will be very, very helpful, and we'll get to that in a minute. So let's look at these. So if I equals square root of -1, if I squared both sides, the radical and the exponent go away, and we're left with -1. So that's where they get this one. I cubed is -I, because I cubed is I squared times I, right? I squared is -1, and -1 times I is -I. Okay, I to the 4th. I to the 4th is the same as I squared times I squared, which is -1 times -1, which is a +1. So that's where those came from. Now, what can we do with that? All right, so again, this is just your little tidbit of information. If I went to simplify I to the 30th power, okay, what does that look like? What does that equal? What I do is I take 4 into 30. So 4 goes into 30. How many times? 7 times, with how many left over? 2. I squared equals -1. Therefore, I to the 30 equals -1. That works for everything. I to the 11th power. How many times does 4? It's always 4. How many times does 4 go into 11? It goes into it 2 times, with how many left over? 3 left over. So the answer to I to the 11th is -I, which is right there. Okay, if I have I to the 40th power, how many times does 4 go into 40? Now, if it goes in there evenly, how they got on there, if it goes in there evenly, then it's this one here. So it equals 1. So whenever 4 goes into, say, 24, it goes in there 6 times. So the answer is going to be whatever I to the 4th is. Since you don't have a remainder, you just take that I to the 4th. Okay, so that's how those work. What I usually suggest students do is to take this table and write it in the front of their book so it's there, so that when it comes up later, you've got it to refer back to. One of the things that's important as far as complex numbers is every single complex number can be written in this format. And basically what that means is A is a number, B is a number, and I is the imaginary part of that number. So you can really write any number this way. You could take a number like 6, and that would be 6 plus 0i. This we don't show. It'd just be the 6, because 0 times I is 0. We can write pi as pi plus 0i, because that goes away. Okay, so everything can be written that way. So we've got 3 different ways to categorize numbers. We've already talked about real numbers. Remember how I make that double line for real numbers? Real numbers are basically numbers that you can put on the number line. Compound numbers are numbers where we have a regular number plus we have the imaginary part of the number. So square root of 5 minus I, those are all compound numbers. Okay, pure imaginary numbers are when you've got a plus bi, where the a is 0. So we end up with maybe 4i, 3i, negative 5i, square root of 7. I mean, all of these numbers are pure imaginary numbers because there's no number that is not imaginary added to it. See, because these are multiplied by I, the whole thing is imaginary. So anyway, let's just keep going. Actually, we're ready to start part C, bottom of page 556, equality for complex numbers. And this is going to get into some tricky stuff. So let's go ahead and save that for the next video.